Hello and welcome to this revision session for GCSE Combined Science Physics Paper 1. So in today's revision session we're going to look at answering examination questions from GCSE Combined Science Physics Paper 1. So if we've been successful and learned in today's revision session, we should be able to answer GCSE Combined Science Physics examination style questions, be able to assess your own understanding on GCSE Combined Science Physics, and then finally understand what topics we need to improve upon for GCSE Combined Science Physics. So the first thing we're going to do is prepare ourselves for this revision session. So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in the left hand side write down any working out or answers to the questions in this revision session, and when you're doing this make sure you write out your answers in full sentences and show your working out. Whilst in the right hand side write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session, and at the end of the revision session write up these notes into a revision sheet for you to use independently. So let's start with some questions, and the first topic we're going to look at is electricity. So the first question is: the lamp is connected to a 24 volt power supply. The current through the lamp is 1.5 amps. Calculate the power of the lamp when power equals potential difference times by current, and then LED lamps are much more efficient than filament lamps. What does that statement mean? So pause the video now, then unpause the video when you want to go through the answers. Right, so in this first one, what's always good is to write out the equation again, then pop in the numbers that you know from your question, and then find out what the answer is by using your calculator. So we know power equals potential difference times by current. We look at the question and the power is the potential difference is 24 volts and the current is 1.5 amps. So you do 24 times by 1.5, you put that into your calculator, you press equals, and you get 36 watts out. Now in this next question you need to know what we mean by the term efficiency. So efficiency is how much useful energy out you get compared to how much total energy you place into the object. Now if you've got a high efficiency, it means you've got lots of useful energy per total energy in, or very little waste energy out compared to total energy in. So from the options present, the answer would be the LED lamps waste a smaller proportion of their input energy than filament lamps because they're much more efficient. Next question: draw a diagram to show how 1.5 volt cells should be connected to give a potential difference of 1.5 volts. Use the correct circuit symbol for a cell. So pause the video now, then unpause the video when you want to go through the answers. Right, so what's important here is you memorize what the different circuit symbols are. And when you connect batteries together to give an overall potential difference, you need to put them in series with each other, all in the same direction. So you've got to have the correct circuit symbol for a cell, which is one small line connected to with one large line next to it, and have all three next to each other in series in the same direction, as 1.5 plus 1.5 plus 1.5 is equal to 4.5 volts. Let's look at the following question. The plug of an electrical appliance contains a fuse. What is the correct circuit symbol for a fuse? Then the appliance is connected to the mains electrical supply. The mains potential difference is 230 volts. Calculate the energy transferred when 13 coulombs of charge flow through the appliance, and use the equation energy transferred is equal to charge flow times by potential difference. So pause the video now, then unpause the video when you want to go through the answers. Right, so it's always, once again, very important that you memorize the different circuit symbols. Now this is just memory and knowledge you've got to have. Now the top box is showing us a LDR, or light dependent resistor. The third one down represents a diode, and then the fourth one down represents a thermistor, whilst the second one down represents a fuse. Now in the next question in our calculation, once again what we're going to have to do is place our numbers in the equation and then work it out with our calculator. So energy is equal to charge flow times by potential difference, so it's 13 coulombs times by 230 volts, so it equals 2990 joules. Right, let's look at the next question. Figure 9 shows the structure of a fuse. Write down the equation that links charge flow, current and time. Then the fuse wire melts when 1.52 coulombs of charge flows through the fuse in 0.40 seconds. Calculate the current at which the fuse wire melts. So pause the video now, then unpause the video when you want to go through the answers. Right. So it's very important you learn your key equations for GCSE Combined Science Physics, because if you can't remember the equation, well, you then can't answer the next question because you need to use that equation. So to remember, it is current is how quickly charge flows. So current is equal to charge flow over time, or charge flow is equal to current times time. Now you are also allowed to write it in symbols. So the symbol for charge is Q, the symbol for current is I, the symbol for time is T. So Q equals IT. So now we need to work out the current. So we can say that if charge equals current times by time, we need to get current by itself. So current by itself means we've got to divide the right hand side of the equation by time, and we've got to divide the left hand side of the equation by time. So current is going to equal charge flow over time, and then we pop in our values. So it's 1.52 divided by 0.40 equals 3.8 amps. Now a couple of things when you're answering these types of questions. The first thing that AQA suggests that you do is actually write out the equation without rearranging first, and then pop in the numbers, as this will allow you to get a mark for identifying that you know what value in the question is charge and what value is time. So they've said 1.52 is equal to current times by 0.40, then they've worked it out, and then the last thing to do is check, does your answer look sensible? So does 3.8 amps look like a sensible number? Well, it does, because that's roughly what it will be in the house, in the mains household. Now let's look at the next question. Answer the following question. Write down the equation that links energy transferred, power and time. Then the power output of the immersion heater is 5,000 watts, and calculate the time taken for the immersion heater to transfer 4,070,000 joules of energy and give the unit. Right, so pause the video now, then unpause the video when you want to go through the answers. Right, so first thing we've got to do is we've got to learn our equation for energy transferred, power and time. So you can either say energy transferred is power times time, or power equals energy transferred divided by time. You can use your symbols, so E equals P times by T, or P equals E over T. Now the next one is calculate the time taken to transfer the amount of energy with that power output as such, like this. So what AQA suggests you do again is let's have our equation of P equals E over T. What we then do is we pop our numbers in. So we say 5,000 is equal to 4,070,000 over time. We then rearrange and make time the subject. So if you notice, to get time by itself, you're going to have to take time from the dividing side on the right hand side to the multiplication part on the left hand side, and then to get rid of the 5,000 you need to then take that from the multiplication side of the left hand side to the division side of the right hand side. So ultimately you get T is equal to 4,070,000 over 5,000, which equals 814. Now you then got to remember to have your units for time. Now what are the consistent standard units for time? Well, they are in seconds. So it's 814 seconds, which once again, does that sound sensible for a heater? Yes it does, so it's probably right. Next question. A student investigated how the resistance of a piece of nichrome wire varies with length. Figure 3 shows part of the circuit that the student used. Describe how the student will obtain the data needed for the investigation, and your answer should include a risk assessment for one hazard in the investigation. So pause the video now, then unpause the video when you want to go through your answer. Right, so let's have a look at our answer. Right, so what do we know? For writing up our experiment, we need to think about the following. We need to think about what are we varying as the experimenter? What is our independent variable? We've then got to think about what are we're going to measure. What's our dependent variable? What devices are we going to use to take our measurements for the independent dependent variable? And how are we going to get some accurate, reliable answers? And what is our hazard as stated in the question? So we're going to be measuring the length, and we vary our length, so give some standard values. So say 10 centimeters, 20, 30, 40, 50, 60, 70, 80 centimeters. You would then say you would measure the length with the ruler. You're then going to measure current and measure potential difference, because we want to work out resistance, and resistance is potential difference over current. So if you look at the information here, you would say you would add a voltmeter into the circuit to measure the potential difference. You then add a ammeter in the circuit to measure the current. You can then ensure you're going to work out resistance by doing potential difference over current, and then plot a graph of resistance against length. Now it's important to think about what can we do to increase the accuracy of our experiments. If you want 6 marks in these types of writing up an experiment, you need to think to yourself, how can I make my experiment accurate? So you could say you will only turn the circuit on when you're taking a measurement, or you could say you'll carry out repeats and work out an average. Both of those ideas would increase the accuracy of your results. Now finally, what is a hazard? So you would have a high current is the hazard, and that can cause the wire to melt or get hot or overheat, which can cause burns to the experimenter skin. So as a result, you would use lower currents when taking the values, you would turn off the circuit when you're not using it, or you would handle the wire with a glove to ensure that you don't get burnt. Next question. The graph shows how the electrical current through a 12-volt filament bulb varies with the potential difference across the bulb. Explain why the resistance of the metal filament inside the bulb changes as the potential difference across the bulb increases. So pause the video now, then unpause the video when you want to go through your answer. Right, let's have a look then. So firstly, what is resistance and what is potential difference? Well, you've got to think to yourself, well, potential difference is how much energy the electrons have per charge moving through the wire, whilst the resistance is caused by the electrons colliding with the metal ions of the metal filament. So what we know is if we increase the potential difference, you'll see from the graph we got more energy per charge, so the current of the electrons, how quickly they are moving through the wire, will go up. Now that means that if they are going through the metal wire faster, this increases the number of collisions between those charges of the electrons and the atoms or ions in the wire. Now this will cause the ions in that metal wire to vibrate more, which will overall increase the temperature of the metal wire, because the temperature of something is basically how much kinetic energy it has. So if the metal ions are vibrating more, they have more kinetic energy, so they have a higher temperature. Next question. A distiller is connected to a mains by a 3-core cable. The wires are covered by different coloured insulation. What colour is the insulation covering each of the wires, and which statement gives the purpose of the earth wire? So pause the video now, then unpause the video when you want to go through your answers. Right, so you've got to just know the colours of the different wires in the plug. Now how I remember it is the second letter of the colour gives you the position of the wire in the plug. So on the left hand side, L, BL, blue. So on the left hand side, which we know is the neutral wire, it must be blue. Now we've got the live wire on the right hand side, which is BR, R for right, brown, BR, so the live wire is brown. And then finally the earth wire is at the top of the plug, ST, striped. So it's green and yellow stripes. So you've got to just know those particular colours. Now what is the purpose of the earth wire? Once again, you've got to know the use and purpose of each of the wires in the plug. So the live wire will provide the potential difference and make the circuit be live. You've then got your neutral wire to complete the circuit, and so it provides a connection to complete that circuit. And then finally the earth wire stops the casing of the appliance becoming live. Now remember, in this context, becoming live means it can give you an electrical shock. Next question. The heating element has a power of 2.5 kilowatts. The resistance of the heating element is 17 ohms. Calculate the current in the heating element. Give your answer to 2 significant figures. Write down any equation that you use. So pause the video now, then unpause the video when you want to go through the answer. Right, so if it's a 5-mark question, it means you're going to need to use quite a complicated equation or multiple equations, and you're going to have to check for prefixes in your question. So if I look in the information given, the power is given as 2.5 kilowatts. Now kilo means 1,000, so the power is 2,500 watts. Now we should know that the equation for power with current and resistance in is power equals I squared R. So if we rearrange it, we know that I squared is going to equal P over R. So I is equal to the square root of P over R. So I is equal to the square root of 2,500 over 17. We work that through and get 12.12678812. Now we've got to then have it to two significant figures. Now remember, you start counting the significant figure with the first non-zero number you see in the value. So we've got 1, 2, they are both non-zero numbers, so therefore we start counting our significant figures at the value of 1 at the start there. So two significant figures is 1, 2, so the current is 12. And there is your answer for that particular question. A student investigated how length affects resistance of a wire. Figure 1 shows the circuit the student used. The student took measurements using meters X and Y. Name meters X and Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's important to note that we always place ammeters and voltmeters in circuits to measure resistance, because resistance equals potential difference measured with a voltmeter divided by current measured with an ammeter. Now how I always remember it is VIP. Voltmeter goes in parallel. So the Y meter is in parallel, so it's the voltmeter, whilst X is in series, so it is the ammeter. Next question. Write down the equation that links current, potential difference and resistance. Then the potential difference across a piece of wire is 2.1 volts. The current in the wire is 0.30 amps. Calculate the resistance of the wire. Write down any equation that you use. So pause the video now, then unpause the video when you want to go through your answers. Right, so again, it's of paramount importance that you write out the equations and learn the equations and link all the different values together in physics. So with this one, V equals IR, so potential difference equals current times by resistance. Now, the next one is as follows, okay? You've then got to think about the following equation, okay? So potential difference equals current times by resistance. So resistance is therefore equal to potential difference over current. So we know that resistance is therefore going to equal your value for potential difference 2.1 divided by your value for current 0.30, so we get our answer to be 7.0 ohms. Now again, we wrote that to two significant figures because potential difference is given to 2 sig fig 2.1 and current is given to 2 sig fig 0.30. Remember, we start a significant figure counting at the first non-zero number. The next topic we're going to look at now is atomic structure. So let's look at the following question. Americium-241 is an isotope of americium. Which of the isotopes given in table 1 is not an isotope of americium? Give your reason for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so the important thing to note is that an isotope by definition is the same atomic number but different mass number. Same number of protons, different number of neutrons. So we look at americium and we know that it has an atomic number, a number of protons of 95. It's the smaller number or the bottom number on your symbol. So therefore the one which is not an isotope of americium is going to be B because it has the incorrect atomic number or the incorrect number of protons. Next question. Figure 5 shows how the number of americium nuclei in a sample changes with time. How many years does it take for the number of americium nuclei to decrease from 10,000 to 5,000? And what is the half-life of americium-241? Right, so let's have a look to see if we can do this. But first, pause the video and then unpause the video when you want to go through your answer. Right, so what would you do here? So you look to see where it starts as 10,000 on the graph. So it starts at 10,000 at 0 time in years. Then you look across to 5,000 and go down, and you see that it has 430 years because it starts at 0 for 10,000, 5,000 comes down at 430, so therefore the difference between the two is 430 years. Now what's the half-life for americium? Well, you've got to know that the half-life is the time it takes to fall by 50% of its value. Now going from 10 or half, so 10,000 to 5,000 is an example of it halving. So actually what the answer you've just worked out before is the half-life, because any time it takes to half its value, so from 2 to 1, 1 million to half a million, 20,000 to 10,000, or in this case 10,000 to 5,000, it is the half-life. Let's look at the next question. Carbon-14-6 is a radioactive isotope with a half-life of 5,730 years. The sample from carbon-14-6 from the fossilized tree gives a count rate of 20 decays per second, and the tree died 17,190 years ago. Determine what the count rate of the isotope was when the tree died. So pause the video now, then unpause the video when you want to go through the answer. Right, so the first thing you need to do is work out how many half-lives there were. So if we notice that it tells you that one half-life is 5,730 years and it died 17,190 years ago, you divide that bigger number by the number for one half-life and you get your answer out to be 3 half-lives. Now the next thing, it's very important, is what does a half-life tell you? It tells you the time in which the count rate or the activity or the number of nuclei halved. So the number doubled when you go back in time, because it's half and going forward in time, so it's double and going back in time. So it starts at 20, so at the start of that half-life cycle it was at 40. Before then it was at 80, and before then it was at 160. So therefore our answer is 160 decays per second. There are 2 isotopes of carbon, carbon-12-6 and carbon-14-6. Describe 2 similarities and 1 difference in the atomic structure of the 2 isotopes. Refer to the number and type of subatomic particles in each isotope. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, what is the definition of the isotope? It's the same number of protons but a different number of neutrons. And remember that in any atom, there's the same number of protons as there are electrons as well. So similarity 1, they'll both have 6 protons. You can tell that because the bottom number of both of them is 6 and the bottom number is the number of protons. The other similarity is they therefore must both have 6 electrons, because in an atom there's the same number of protons as there are electrons, but carbon-12 will contain 6 neutrons and carbon-14 will contain 8 neutrons. Now why is that? Well, the top number, the bigger number, is going to tell you the number of protons and neutrons. So you know in the left hand side isotope that there are 12 protons and neutrons and 6 protons, so therefore there must be 6 neutrons. And in the right hand side isotope there are 14 protons and neutrons but 6 protons, so only 8 neutrons there. Right, let's look at the next question. The half-life of carbon-14 is 5,730 years. Carbon-14 is used for carbon dating. Carbon dating can tell us how old some objects are. A skeleton was carbon dated. The results show that there was only 12.5% of the original amount of carbon-14 left in the skeleton. Calculate the age of the skeleton. So pause the video now, then unpause the video when you want to go through the answers. Right, so first thing you need to do is work out how many half-lives have taken place to get to 12.5%. Well, if you think about it, you're going to start off when it's 0 years at 100%. So you then do 100 divided by 2 is 50%. 50% divided by 2 is 25%, and then 25% divided by 2 is 12.5%. The tip is, if you ever want to work out how many half-lives you've got, you start with your original number and keep dividing by 2 until you get to the number you want to, which in this case is 12.5. So therefore, we can therefore see that 12.5% gives us 3 half-lives. Now, one half-life is 5,730 years, so therefore 3 half-lives is 17,190 years. Next question. Explain why irradiating food makes it safer to eat. Food is packaged and then irradiated. Explain why food is irradiated using gamma radiation rather than alpha or beta. And some people are concerned that irradiated food could be radioactive. Describe how irradiated food is different from food that is radioactive. Pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand why we irradiate food. Now, irradiation, with certain types of radiation, can actually kill off bacteria. So that prevents food poisoning because it kills off the bacteria or microorganisms and that which will produce toxins which can lead to food poisoning. Next question. Right, why do we use gamma radiation rather than alpha and beta? And it's important you know the properties of alpha, beta and gamma. Well, gamma is the most penetrating radiation, so it can pass through all the packaging, and it's also the least ionizing of the radiation, so it'll pass through without damaging the food. Now finally, okay, if you look on here, what's the difference between irradiation and from food that is radioactive? Well, irradiation is when you are exposed to an external source of radiation, when radiation passes through you, whilst radioactive food is something which must contain unstable nuclei or a source of radiation, or it's given off radiation itself. So being irradiated is having radiation passing through you, but being radioactive means you're in fact giving off radiation yourself. It's very important you know your definition of irradiation and how it can then link into contamination as well, and what makes a substance radioactive and what doesn't. Let's look at the next question. An isotope of carbon-14 can be shown as 13 carbon-6. Figure 12 shows the incorrect diagram of the structure of this atom. Explain why the diagram of the atomic structure shown in figure 12 is incorrect. So pause the video now, then unpause the video when you want to go through your answers. Right, so again, you've got to know what the top number and the bottom number means. So the bottom number is the number of protons, but also for an atom, it will be the number of electrons because it's the same number. And then the top number is the number of protons and neutrons together. So therefore we can work out here we should have 6 protons, 6 electrons, and we should have 13 minus 6 neutrons, which is going to be 7. So what we should see is as follows. We should have the following idea that we should have 6 electrons in the outside of the atom, and we don't. We actually have 7. So that's an issue. And secondly, you should know from chemistry that in that first level, that first shell closest to the nucleus, there can only be 2 electrons, and there's 3 here. So there's another issue. Then next you look here and we find only 5 protons, not 6. We know this because there are only 5 pluses. So as a result, we should have 6 protons, and we should actually have 7 neutrons, but we don't. We have it the other way around. We have 5 protons and 8 neutrons. So the issue are we should only have 6 electrons in total, with 2 in the inner shell. Well, there should be 1 more proton because there should be 6 protons, and there should be 1 fewer neutron because there should only be 7 neutrons. Let's look at the next question. Figure 10 shows how the count rate detected from the radiation source and the smoke alarm changes with time. The smoke alarm switches on when the count rate falls below 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. So pause the video now, then unpause the video when you want to go through your answers. Right, so the idea is that if you have a long half-life, it takes a long time for the count rate to half. So a long half-life means the count rate is approximately constant, or a short half-life would mean the count rate decreased too quickly. Now you'll notice here that from our graph, if you look at this, because you should always relate information from the graph into your answer from the question, that there's only about 1.3 half-lives where the count rate is above 80 counts per second, or 1.3 half-lives before the smoke alarm gets activated. So you want a long half-life so that you don't have to replace your smoke alarm as quickly as you would do otherwise. Let's look at the next question. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm. The smoke alarm stays off while the alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing, and why is it safe to use alpha radiation in a house? So pause the video now, then unpause the video when you want to go through your answers. Right, so you'll notice that from the diagram, but also from your knowledge, alpha radiation gets stopped very, very easily. So why does it switch on? Well, as the smoke air goes into the casing, it stops the alpha radiation, so they can't get to the alarm circuit, and that sets off the smoke alarm. Why is it safe to use a source of alpha radiation in the house? Well, you've got to know your properties of alpha radiation. Alpha radiation is not very penetrating, or it doesn't go through the skin, or it doesn't travel very far in the air, so it's very unlikely to encounter the insides of a human. Next question. Some street lamps contain sodium. Figure 5 shows two isotopes of sodium. What are isotopes? And how many protons and neutrons are in the nucleus of 2311 sodium? So pause the video now, then unpause the video when you want to go through your answers. Right, once again, you've just got to know the definition of an isotope. And an isotope are atoms with the same number of protons, which tells you what element it is, so it's the same element, but a different number of neutrons. You can tell that because the bottom number is the number of protons. So in the second question, there are 11 protons and 11 electrons, because there's the same number of protons and electrons in an atom, but the number of neutrons is 23 minus 11, because 23 is protons and neutrons, whilst protons are it's just the bottom number. So it's 23 minus 11, which is 12. Next question. Figure 5 shows how the activity of radium-226 will change. Determine the half-life of radium-226 and show you're working out on figure 4, and radium-226 was discovered by Marie Curie in 1898. The notebooks you used were contaminated with radium-226 and are still hazardous. Explain why the notebooks are still hazardous. So pause the video now, then unpause the video when you want to go through the answers. Right, so again, you're going to have to draw on your graph to show you know where half-life is. So the trick you would do is you would look and you would see where are we starting at 0. So we're starting at 0 if you look at the value at about 184,000. It's slightly above 180,000. You'll see that, so it's about 184,000. So what's half of 184,000? 92,000. So you draw a line from 92,000 across to the graph and then look down, and that will tell you your half-life with time in years. So you get an answer of 16,000 years. Now that leads into the next question, because why are the notebooks still dangerous today, even though Marie Curie carried out this work in 1898? Because there have only been a certain number of years past, so we are currently in 2021. So for this one, there's 121, I can't get that right, sorry. There's going to be 123 years that have passed since that point. Okay. And the activity will not have dropped by that much because it takes over 16,000 years for it to drop by a half, so it won't have carried out much in that time being elapsed. Let's look at the next question. Explain how the properties of alpha, beta and gamma radiation affect the level of hazard at different distances. Pause the video now, then unpause the video when you want to go through the answer. Right, so it's very, very important you know the properties of alpha, beta and gamma, and then you can link this into the hazard. So what do you know about alpha radiation? Well, alpha is the least penetrating of the radiation, so it has the shortest range in air, but it's the most ionizing out of the radiation. Now beta is the second most penetrating, but also the second most ionizing, so therefore it will have the second longest range in air, whilst gamma is the most penetrating, so has the greatest range in air, can travel the furthest, but gamma is the least ionizing. It's going to cause the least amount of damage. So it tells us that at short ranges where all three are present, alpha being the most ionizing, is the most dangerous. At the middle, now, alpha's gone because it can't travel that far, so you're left with beta and gamma. Now, beta is more ionizing than gamma, it's more dangerous than gamma, so beta becomes that most dangerous at the middle range. But whilst at longer ranges, only gamma is present because alpha and beta can't travel that far, so because gamma is the only one left, gamma is the most dangerous, even though it's in fact the least ionizing of the three radiations. So, that concludes our revision session today on the topics which we've covered for GCSE Combined Science Physics, which have included electricity and atomic structure. So hopefully you can answer GCSE Combined Science Physics examination style questions, you can assess your understanding on GCSE Combined Science Physics, and finally you understand what topics you need to improve upon for GCSE Combined Science Physics. Thank you very much for watching this revision session, and as always, have a lovely day.